Hi guys, welcome back to another TMUA question. Today we're going to be doing TMUA 2016 paper 1 question 5. It looks like a pretty easy one, so let's get started. Okay, so we need to find the area enclosed between the curve y equals x squared minus 1, the x-axis, and these lines, x equals minus 2 and x equals 2. Okay, so first let's draw a rough sketch of this graph. It's going to be your y-axis, there's going to be the x-axis, and we're going to have y equals x squared moved down by 1, so it's just going to be like that. Now also, let's just really quickly find the root of this equation. We're going to have sorry, let me wrap this out. We're going to have x plus 1, x minus 1 equals 0, so we're going to have x equals 1 and minus 1. So over here, we're going to have x equals minus 1, and over here we're going to have x equals 1. Let's draw in the lines that they asked us for. They said x equals 2 and x equals minus 2. So let's just add those in here. Looks like I'm going to have to redraw this quadratic. It's going to be something like that. Okay, now what you might think we need to do is just simply integrate this expression between minus 2 and 2. But you need to notice that over here we have an area that's below the graph. So integrating this expression would give you the sum of this area plus this area minus this area, which is not what we want. We want this area, we want this area plus this area plus this area. So to do that, we split it up into either 2 or 3 separate intervals. If you want to split it up into 2 separate intervals, as I noticed, you must first notice that y equals x squared minus 1 is symmetrical about the y-axis. So I could just find the area under the graph on the left side or on the right side and double it, and I'll get the total area that it makes with that the graph makes with the x-axis between x equals minus 2 and x equals 2. However, an alternate method is just the brute force approach, or where you find this area, and this area with 3 separate integrals, and yeah, yeah. However, that's a more tedious approach, and we want to save as much time as we can here. So I'm going to go with my approach. So the first integral, I'm going to take the right side just for the sake of using positive numbers, so it's easier. Over here, I forgot to label it, we have 2 and minus 2. So to I'm going to need a different color. To find this area here, I'm going to use the integral of x squared minus 1 between minus 1 and 2. I mean 1 and 2, sorry. 1 and 2 dx. Integrating this should be pretty easy. We're going to have x cubed over 3 minus x with the limits 2 and 1 still. So it's going to be 8 over 3 minus 2 minus 1 over 3 minus 1, which is going to be 2 over 3 minus 2 over 3, which equals 4 over 3. Okay, so now we have this purple area over here. So now what we need to find is this area here between the y-axis and 1. So that's going to be the same integral. So we don't really have to integrate it again. We could just rewrite. I'm just going to write it for the sake of the video. We're going to integrate from 0 to 1 of x squared minus 1 dx, which I'm just going to use that. It's going to be from, I'm just going to substitute these limits into this. It's the same integral. We're going to have 1 cubed over 3, which is just 1 over 3, minus 1. And the second integral is just going to be 0, because 0 cubed over 3 is 0, and 0 times and 0 over here is just going to be 0. Just draw that line to separate that. Why cannot? Okay, so this is going to be 1 over 3 minus 3 over 3, which is minus 2 over 3. The reason the answer is negative is because this is below the graph. So instead of using it as a negative value, which is what would have happened if you did not split up the integral into 2 or 3 separate integrals. So I'm going to take the positive value of this, which is going to be 2/3. So now I need to take this 4/3, take this 2/3, then 4/3 plus 2/3, which equals conveniently 6/3, which is 2. And now, since we said we need to double this answer, due to the approach I chose to take, 2 times 2 is 4, which means that the answer is C.